Welcome back. So let's continue with a new part of the lecture, and we are just making progress in our technology stack. So let's look at what we have so far. So we started the entire course with a brush up of SQL and relational databases and PostgreSQL, which we'll also have that at the exam, the PostgreSQL part. We saw that there is a relational algebra with projection, selection, joining, grouping, sorted, and so on. We saw that we even have a syntax in which we can actually store flat tables, right? So those that satisfy relational integrity, atomic integrity, and domain integrity. We can store that as CSV. And we saw that logically it's a table, but physically it's text. And finally, we have a language, SQL, that allows you to query tables. So that are, again, relational integrity, atomic integrity, domain integrity. Then you write SQL, you had a table, and you get another table as the output, right? So it's beautiful. This is the beautiful world of relational databases. But they have a few limitations. First, typically, this kind of database fits on a single machine. So it's constrained by the size of a machine. Second, this needs to be tables, they need to be flat, atomic, and so on and so on and so on, right? So we do have these constraints. Now, if you look at the stack, we have rebuilt a lot of that on larger scales. So now we are not constrained anymore by a single machine. We can have thousands of machines. And we've looked at many of the layers already of this. And as far as tables are concerned, we are in a pretty good state, actually, right? Because you could use, for example, you could store CSV files on HDFS, right? This is a table. You could open them as data frames. You can validate it and open it as valid data frames in Spark. You could even store it in HBase if you prefer, but don't have to. And you can use SQL in order to query them, Spark SQL, for example. So now we have a way to query gigantic, enormous tables that are petabytes long with Spark SQL on a cluster with 10,000 machines automagically. Right? You can write that in your notebook and everything just magically pops up in the background. I'm not saying it takes 5 minutes, right? If you have thousands of machines, you might have to wait for an hour, right? But at least you're productive because you just wrote your SQL lines and that's it, and it just works. So we kind of did well as far as tables are concerned in terms of scalability. We went from a single machine to an entire cluster. But this is the case where we have relational integrity, domain integrity, atomic integrity. And we saw that in the case of big data, we like to break these rules. We like to break relational integrity. We'd like to break atomic integrity with nested structures. And we'd like to break domain integrity even if we don't have a schema. But this we also started looking at in the past few weeks, right? We've done a lot. And in particular, we saw that the solution, syntactically, at least at text, to break the rules, relational atomic domain, is to use a syntax that has a tree logical model, like XML or JSON. So if you have a collection of JSON documents or a collection of XML documents, doesn't really matter which one, then we don't care, we can have nestedness. We don't need a schema if we don't want to. So we can have extra keys, we can have missing keys, that's not a problem at all. And we can even have different types within the same collection, that foo can be an integer or foo can be an array, and it doesn't matter. So we've done a good job at that as well. But we're not there. See, there's still a few question marks in there, and we are not at the point that we can use a language like SQL on thousands of machines on that. So we still have a bit to do on that, but we will get there. At the end of the lecture, we will have a full solution. So in this lecture on document stores, we just continue to move our way forward with this, with document stores. So if I look at the structured stack, right? If you have tables, then you have, of course, in HDFS, you would have bits that are text, that are actually CSV, that is well-formed. CSV, you can see as a relational schema, and you can query them with SQL. If you want to go now to XML and JSON, so to break the rules, then something changes a little bit. The part that changes is that the data doesn't need to have a schema or doesn't need to be valid. It can be valid if we want. If we want to validate JSON or XML, we're going to get data frames, but we don't have to. we can also just take whatever XML or whatever JSON we want, even if it's not valid. It breaks all of the rules, and that would still work, right? So we would like to go all the way to querying XML and JSON, even though there is no schema, even though there are plenty of rules that are broken, right? So there is a tiny difference. Again, in the case of relational tables, there is always a schema. You cannot even put data in there without a schema. In the case of XML and JSON, not necessarily. So we basically would like to build a system just like PostgreSQL, right? But we want to allow something more generic than tables, breaking rules, and we want to scale on thousands of machines. So we need to query trees on thousands of machines. So here's what happens whenever people come up with a new data shape or a new model and they want to build a relational database management system, in that case, trees. The first thing people try to do is to reuse existing systems. It's always a great idea to reuse existing systems because they're cheap, they're even often free, they already work well, and so on. So the first idea that you could have is, what if we can force the trees to fit into tables? Can we do that? People tried. Well, there are cases where it's easy to fit trees into tables. For example, if the tree is flat, in that case, it's respecting atomic integrity because I only have atomic values, right? An integer, a string, a Boolean, a string, a number. So this is a flat database row. Now this is easy, right? I could do it with XML too, right? It's the same. I don't mind. It's also flat, right? It doesn't matter if JSON or XML, right? The same results. Now, if I have two of them, and again, I assume relational integrity. It means they have exactly the same keys. They have exactly the same columns, right? And on top of that, even domain integrity, meaning that I assume that foo is a string, true, false. Here it doesn't complete. Oh, what did I do? That was supposed to be foo2 that's just a small mistake, a small typo. In the second one, it's foo2 because I wanted to also have domain integrity in there, foo being an integer. I'll fix that. But anyway, if you look at the other columns, we have relational integrity, same columns, and we have domain integrity within a column, always the same type. Okay. This is the easy case, right? Who understands this mapping? This is easy, right? We've seen it before, even. Okay. So this is the easy case where we respect all of the rules. We can even map schemas because we saw that we can validate this kind of data with JSON, with JSON schema, with XML schema. Doesn't matter. Here I'm showing you XML schema where foo is an integer, bar is a string, foo bar is a Boolean, A is a string, B is decimal. That should all be familiar to you. And what I get out of that is a SQL schema. I could even write, who could write the SQL code for that to declare a table on this schema, right? We know how to do this, right? So there is a correspondence. Right, I could even write the JSON schema, also do the same. Okay. But the difficulty is when you start breaking the rules, because this is a very specific case. This is the case against where we have the three rules. But if you start breaking the rules, first you're going to get nestedness. You can have tables in tables, and you're going to have heterogeneity with mismatching types, with extra columns, with missing columns. So nestedness and heterogeneity are the two things that are pushing us out of our comfort zone with the good old relational tables. And this is the beautiful world of NoSQL. NoSQL across time has had different meanings, but now I think people accept it as meaning not only SQL. It's not a competitor of SQL or saying SQL doesn't work. It's just not only SQL, meaning there is something else than just SQL and relational tables. Right. Take a snapshot of this in your brain. Heterogeneity, nestedness, super important. These are the two things that we want to push on the limits. Now, in some cases, if we want to force this into table, it's going to work, right? Like, for example, here I have something that I could even write a schema about, right? It's just a nested sequence of objects nested in an array, nested in the top object, right? That I could still store in tables, right? I just need to normalize things. I need two tables, one table for the top level in yellow and one table for the nested level. And I can paste them back together with a join, right? I can join the category columns and I get back mathematician with Ramanujan and Gödel, and I get back physicist with Einstein, right? With 1, 1, and 2. Who sees that? Right? So this is, again, an easy case where I can actually fit that into several tables. I need several tables, but it works, right? What about this? So this is the case of nestedness, but organized nestedness, right? I still have a schema. Now, what do I have here? I'm breaking relational integrity. So I have extra columns, missing columns, and so on. Can I fit that in a table? Yes. If I force it and hit it with a hammer, I can fit that in a table. It's just that I'm going to need some nulls in the table, right? Whenever I'm missing something, I put a null. This is not very nice. It works, but it's not very nice, especially if you end up with a table filled with nulls everywhere. It's not very efficient. In the end, what you quickly realize, especially if you try to deal then with data that is with type mismatches and so on, is that you're essentially trying to put a square peg into a round hole. So this just will not work. That's called an impedance mismatch in databases. An impedance mismatch is whenever you try to make something fit into something else, but the types do not correspond, the structures do not correspond. It just means we have reached the limits of the relational algebra and of the of SQL. We need something different. So a new kind of system as part of the NoSQL community emerged with plenty of technologies. They are called document stores. MongoDB is only one of them. And the idea of document stores is that they reproduce something that looks a bit like PostgreSQL, like a database management system, except that they break the rules. So it means that in a document store, instead of requiring that the data is organized in tables, you just require that the data is a collection of objects, collection of documents, or a collection of XML documents, can be anything. So a collection of documents that scales up to millions or trillions. You can even distribute across machines, terabytes, petabytes. But what you have in your collections doesn't need to be rows anymore. It can be documents, including nestedness, heterogeneity, and so on. This probably should have, by the way, a déjà vu, because when I say collection of whatever, we've seen plenty of collections of whatevers everywhere in the lecture, right? We've seen, for example, RDDs are collections of whatever, right? In MapReduce, we have collections of key value pairs. A table is also a collection of whatever. It's a collection of rows. So now you probably start seeing a déjà vu with this kind of large collections, right? But this is great if you do have this feeling of déjà vu. Now, what can the documents be? Well, there's two kinds of products in this ecosystem. There's the people who love JSON and there's the people who love XML. So we have document stores with XML documents and we have document stores with JSON documents. What I would like you to see is that it doesn't really matter, because in the end, it's very similar, and it's very important that you're not too stuck on one side or the other. Just zoom out and just notice it's actually the same, right? But it's true that lately, the JSON document stores enjoy quite some popularity because some people find it simpler. XML is more enterprise ready, so there's pros and cons on both sides. But what you should see is that it doesn't really matter. In both cases, it's just collections of trees, whether XML or JSON. Okay, collections of trees. So that's an example with only 3 trees. Of course, I cannot put 1 million of them on my slide, so I only put 3. But you can see here what it can look like when you put that in a collection, right? So typically, when you have a document store, you can have a lot of documents, but the size of the documents shouldn't be too big, right? So typically, in a system, it can be up to a few dozens of megabytes. 16 megabytes, 64 megabytes is very common. It's actually very close to the size of an HDFS block, actually, in terms of order of magnitude. But typically, systems will not perform well if you start storing gigabyte documents, right? So typically, you need to keep the size of your documents under check. You can really scale to billions, trillions, quadrillions of documents on some of the newer systems, but you need to check that the size of the documents doesn't go too far, right? So a few dozens of megabytes. It's also the same size I mentioned in HBase that you can put in the cells of HBase. You can go all the way to 10 megabytes without losing too much performance, okay? It sounds trivial when I say to you a collection in a document store is a huge number of small documents, but it took me several years to realize that. I mean, I did my PhD a long time ago, and this was still very emerging, but it took me years to finally realize that the whole thing is about the trick that makes everything work is the realization that you scale the number of documents, but you keep each document small. This is simple and incredibly powerful at the same time. Okay. So thousands, millions, billions, trillions, even quadrillions in some systems of documents like that. The trees can be nested or you can have them flat. The document stores will also work if the trees are flat, but they don't need to be flat. And secondly, the document stores will also work if the trees follow the same structure, they follow the same schema, but it will also work if the trees do not have a schema at all, and you have heterogeneity. So again, nestedness and heterogeneity, these are the two things that differ. Now we want a system, if we say we want a system like PostgreSQL, we need to query the data. So we need an algebra, we need a query language, and so on. Now, the people who designed these things, they didn't reinvent the wheel. We reuse the same concepts like selection, projection, aggregation, group by, and so on. But there is one thing that document stores do not do well. They were never designed really for that. It's joins. If you want to join data, the document stores are not going to be the best way to do it. In fact, in some systems like MongoDB, you don't even have an instruction to do joins. In MongoDB, if you want to do a join, you have to implement it yourself. In Java or in Python or whatever. And people actually do implement joins themselves because MongoDB was not designed to handle joins. So it's projection, selection, aggregation. But you know the trick, right? If you cannot do joins, you just denormalize your data because we've seen that denormalization is the opposite of joining, right? So if you don't want to do joins, you just pre-compute the join by nesting your data, and then you don't need to join anymore, right? You just directly deal with the denormalized data sets. Okay. Something also that we have in NoSQL is that unlike in PostgreSQL or relational database, you don't need a schema. If you just drop your JSON documents into the collection, you don't need to validate them, it will just work. In PostgreSQL, that will not work. It forces you to first design a schema before you put the data. So this is a very important difference. And this is also called schema on write in the case of PostgreSQL versus schema on read in the case of document stores, because you only lazily evaluate the schemas if you need them. Okay. There's a whole ecosystem, plenty of document store products that are out there. Some of them are free, some of them you need to pay, some of them are smaller, some of them are established. So just to name a few, there's CouchDB, Elasticsearch, MongoDB, ExistDB, Cloudant, ArangoDB, Cosmos DB, maybe with Microsoft BaseX, MarkLogic, and so on and so on and so on. Right. MarkLogic was one of the enterprise-ready ones that were early. They were actually involved. You might have heard in the US, Obamacare and so on. So they were actually involved in the project. MongoDB are one of the most popular ones. They got rounds of investments in billions of dollars in their early phase. So there was a lot of interest. MarkLogic supports both XML and JSON. MongoDB is JSON, ExistDB. Everything that has an X is probably SQL, by the way. So ExistDB is sorry, not SQL, XML. Everything that has an X is XML. So ExistDB is XML, BaseX is XML, and the others, I think, are JSON. Okay, Elasticsearch is really good at indexing documents that is like language, actual text. It's very good at that with a thesaurus and yeah. Okay, there's a whole ecosystem, but of course I'm not going to go through all of them. We're going to focus on just MongoDB, but you'll see that the principles are very similar. So again, if later you need to learn another one, you will see that it's very, very similar. Okay. So now I'm moving on to showing to you how we actually query data, query JSON or XML in a document store, and how it looks like and how it does not look like a system like PostgreSQL. Before we do that, I would like to emphasize a difference that I've already spoken about, which is the difference between two kinds of systems. There's the systems that are fully integrated, where you just give them your data and they will take care of everything. So PostgreSQL is like this. MongoDB is actually also like this. It means you need to import your data when you want to use it. ETL is just a synonym for importing. You need to import your data. So these are the database systems on the left, basically, good old database systems. On the right, you actually have what's called a data lake. A data lake is just some sort of place where you dump your data the way it is, right? So it's a file system. HDFS, S3, and on top of that, you use Spark and so on and so on. This is all data lake oriented, right? You don't import your data, you just drop it. You just store it on the file system. These are the two approaches. The approach on the left sounds a bit more involved and heavy because you typically have proprietary hidden formats on this, the way it's stored on the disk. PostgreSQL is basically a proprietary format, MongoDB too. But you get benefits because the systems on the left, they are going to be much faster if you look up data. For example, you look for a specific place in your data set, you have billions of objects and you look for one specific object. The systems on the left will be very, very fast because they use something we call indices that we will cover with MongoDB. The systems on the right, they will not be that fast because in a data lake, the way you query a data lake is exactly what we've seen with MapReduce and Spark. How do you query a data lake? You just partition the whole thing and scan through the entire data set in tasks, as we saw, right? The tasks on the slots and so on. So when you are working on a data lake, it takes easily an hour or several hours to actually scan through in the entire data, shuffle the data around and so on and so on and so on. So it's more involved. It's great if you want to aggregate data because then you really need to scan. But if you're looking up for very specific data, then the systems on the left are going to do better. In Spark, let me give you an example. Imagine that you have a data set that is dropped on the data lake, dropped on HDFS, that has 1 trillion JSON objects, and you're looking for a very, very specific object. You're looking for a specific object, I don't know, that has, for example, name Ramanujan, right? How do you do that in Spark? Well, probably you're going to define some filter transformation, right, in Spark. But how is it executed? It's going to scan through the entire data set, everything. And then it's going to filter, and then at the end, you're going to get it. It's going to take hours. But the system on the left, they have index structures that directly give you the results when you look for a specific object. So while we have been focusing on those on the right for several weeks, when we looked at S3, HDFS, HBase, and then Apache Spark and MapReduce and so on, so we've been a lot exploring the data lakes on the right. But this week, we are coming back to systems like PostgreSQL that are based on importing things and so on. But I wanted to say that to make this distinction very clear, the database systems on the left and the data lakes on the right. Okay. Now, MongoDB, as I said, since you import your data, MongoDB is not going to store your data as JSON. There's a good reason for that, is that JSON is very inefficient. Right? JSON is very inefficient. You keep repeating the keys, it's text, it takes a lot of space. So MongoDB is not going to use that. If you pour JSON into MongoDB, it's going to instead internally store it in a format called BSON, like binary JSON. Now you might be asking, why not Parquet? Parquet is great. Parquet doesn't take a lot of space. It's very efficient. And I've told you before, use Parquet if you can. Yes, but Parquet only works if you have a schema. Remember, you validate your data, you have a schema, then you store it as Parquet. But MongoDB has to work also if there is no schema. So this is why we cannot just use Parquet. We need something specific. Right? Okay, but you don't need to know the details, just the name BSON is enough. Okay. Now, what does MongoDB offer? Well, as we will see, it doesn't have a language like SQL, right? That we'll bring in the next few weeks. It has a very simple interface in JavaScript or Python that is based on a paradigm called CRUD. Create, read, update, delete, right? C-R-U-D. So you can easily create documents, you can easily read documents, look them up, you can easily update documents, and you can easily delete documents, right? It's a bit on a lower level than SQL. But I think the best way that I can show you that is with examples. So now I'm going to show you plenty of slides with concrete examples of the way that we are going to use MongoDB. So when you start using MongoDB, I think most people, when they actually learn it at the beginning, they are going to connect to the MongoDB shell. It's a little bit like a Jupyter notebook, but a bit less fancy than that, right? So you can even do it on the MongoDB website. I think they can even show you that in your browser, or you can install it and do it on the command line. And basically, by default, it's a JavaScript shell, right? But you don't need to worry. You don't really need to learn JavaScript that much because the language, I mean, the way you query MongoDB is not so much in the JavaScript as it is in the JSON that you actually put in there. So don't worry, I'm not asking you to learn JavaScript. So basically, it's a JavaScript shell, and then there is some sort of programming interface to do the queries. Now, let me start with one. So assume that I have a collection of JSON documents called scientists. In my shell, I'm going to type db.scientists.find, and then I can put an empty object, or I can even put nothing. That is going to return the entire collection. And then on my screen, you will see it will not show all of them. Of course, maybe the first 10 or the first 100, just telling you, okay, there's more, and that's it. But what would that be in SQL? I put it on the top right. It's a cheat sheet, just for your convenience. It's actually as if I had said select star from scientists, right? That actually doesn't exist. MongoDB doesn't support SQL, right? But just to show you the comparison, what it corresponds to. So select star from scientists, it's SQL cheat sheet. All right. So this is what you get with dbscientists.find. For whom is that clear? That's super easy, just gets the entire collection. Okay. Now, of course, that's here an empty object, but what if you put things in the empty objects? So now, what's nice is that what you put in there is actually JSON. You already know JSON, right? And the query language of MongoDB is based on JSON. So what you put in the function find as the first argument is a JSON that is kind of what you're looking for. So what am I looking for here? I'm looking for the objects in my collection, scientists, that have theory, the key theory associated with relativity. This is what I'm looking for. So I'm just putting in my find function theory relativity. You see, I just put it in JSON. In that case, I have the simple case of 4 documents in my collection. There can be, of course, billions, but just 4 in a slide. I'm going to return the first one and the fourth one, right? Because theory relativity, theory relativity. The second and third one, no, because theory is something else, right? Who is following? Okay. Now, if you look at SQL, the equivalent, that would be a where clause, right? It's as if I was saying select star from scientists, where theory equals relativity. What is this called in the relational algebra? What did I just do? Was it a projection? Was it an aggregation? What was this? Anybody? I think I hear it very, very quickly. Yes, a selection, exactly. This is a selection. So the first parameter in find is a selection based on the JSON criterion that you pass to it. Okay. There's a second argument that is optional. So here there was no second argument, but you can add a second argument. The second argument is a projection. So the second argument says, I want first and last. So I'm projecting my data on first and last. So now I'm getting first Albert Einstein and first Hermann, last Minkowski. In SQL, it's as if I said select first last from scientists where theory relativity, right? So I have both a projection and a selection here. So again, the first parameter is kind of the where clause in SQL, and the second parameter is kind of the select clause, right? So the where clause does a selection, and the select clause, unlike its name indicates, does a projection. Okay. So in fact, what we are doing here is not so far away from SQL, right? It is a simple case where the data is actually structured. Here, I'm going to do something that SQL can actually not do. There is nothing there. It's projecting away. What if I want to output the results of my query, but I want to remove columns? I want everything except theory. Well, then I just put a 0. Instead of the 1 here, I put a 0, and this is going to exclude the column, okay? Now you might ask me, okay, why is there no SQL equivalent for this? But it's because in SQL, we don't need an equivalent. Why? Because in SQL or in PostgreSQL, you know the columns. You know the columns from the schema. So if you want to project away theory, if you know that the schema is first, last theory, then you just do this. You just say select first, last, right? Because you have the luxury of knowing the schema. But in NoSQL, in general, you don't know the schema. So actually, if you don't know the schema and all you want to do is remove theory, then you don't have a way to do that with just once, because there is no way you can list the other columns. You don't know them, right? So this is why now you can do this that you couldn't do in SQL. Okay. Okay. Now, how do I have multiple criteria? That's basically an end in my where clause, right? Where theory is relativity and last is Einstein. Well, I just add more keys in my JSON object in the find function, right? So here I'm requesting for the theory being relativity and last to be Einstein. What about or? Well, or is a bit more involved, right? Because by default, if I just put them in my object, it's going to be an and. If I have an or, then it's more complex. And this is basically where you start seeing that it's a bit annoying, because that doesn't have the beauty of SQL. This is really not a SQL-like language here. This is just an API in JavaScript. So don't be scared, right? We will have later something that looks more like SQL. But basically, the idea is that in MongoDB, you have special instructions with the $ sign. $or is an example of them. They are treated specially. And $or basically takes an array with all the filters that you want to apply, but with a semantic of or. So you want last to be Newton or last to be Einstein. In SQL, that would have been where last Newton or last Einstein. Right? Okay. What about comparisons? Here too, again, I told you, don't be scared. If we want publications greater than or equal to 100, in SQL, we would just have said publications greater than or equal to 100. In MongoDB, we just need to nest JSON. And again, it's this $ thing that makes it special. So here, instead of saying publications is something, we just put an object that says that something must be greater than or equal, GTE, than 100. And now I'm going to get the first and the third documents. Who is following? Okay. Now, let me say a few words on heterogeneity, because unlike PostgreSQL or good old relational systems, the collection we're looking at might be heterogeneous. You might have some objects that have more keys, you have some objects that are missing keys, some objects that might have different types, and so on, right? So I have an example of missing field in my 5th object. I have needs_bor, but there is no theory key in here. And I have a case of other type for Isaac Newton, theory false. I just put random stuff in there. But basically, otherwise it's a string, right? Relativity, incompleteness, relativity. But here I put a Boolean. So this is an example of heterogeneity. In MongoDB, it's totally fine. You can absolutely do that. In PostgreSQL, you couldn't. There is no way you can do this in PostgreSQL. Well, you could put a null technically for the missing field, but this false here in PostgreSQL, you can't do that. But in MongoDB, if you filter for theory relativity, it's not going to complain that it's not always a string. If it's not a string, it's just ignoring it, right? So it's ignoring Isaac Newton, it's ignoring Niels Bohr, and it's just going to return Albert Einstein and Hermann Minkowski, right? So you see how this is more flexible than SQL in that regard. I still put an equivalent SQL query, but again, keeping in mind that in SQL, you could not have the heterogeneity. Okay. What if I want to specifically ask for the theories that are missing, right? Then I just put a null here. Why can I do that? Well, it's because MongoDB is making an assumption, and not everybody is assuming that, but MongoDB is assuming that having a missing key or having the null value is the same, right? So if you say theory null, it's looking both for theory null or theory missing, right? just be aware that not everybody agrees with that convention. There are other systems that treat a null value and a missing value in a different way, but in MongoDB, it's the same. It's considered equivalence, right? So this is the reason why when you say theory null, it's going to return the fifth object, because theory is actually missing. Okay, so this addresses heterogeneity. What about nestedness? What if our collection has nested objects or nested arrays? Well, this is where the dot actually comes in handy. Because if we want to actually look up inside an object, for example, what if I'm looking for an object that has, so within the key name, and then within that, I want another object with the keys first. There is a key first, and then it's Albert. So what does that match? This is what it's doing. If you say find name first Albert, this is going to return the first one. You see first nested inside name, and the second one too, Albert Zweistein, also look, nested inside name, but not the third one, because name.first would be Kurt. Here. So what do we learn from this slide? We learned that not only the dollar sign is treated in a special way, but the dot is also treated in a special way, right? Because otherwise, if the dot wasn't treated specially, we would really be looking for a key that is actually named dot first, right? But the dot is treated in a special way, and this is why it's interpreted as navigation. Okay. And this is a common pitfall that some people make that mistake, that they think, okay, if I want to look for Albert associated with first within an object associated with name, some people might want to write that. That doesn't work. That doesn't do what many people think it would do. If you write this instead of using the dot, it's going to try to look for exact matches. It's going to look for an object associated with a name that is exactly first Albert. Nothing more, nothing less. Exactly first Albert. So in that case, it's going to return the second document because that's exactly first Albert in there. The order doesn't matter, of course, but exactly the same. But the first one would not be returned. Why? Because it also has last Einstein. That's not an exact match, right? So be careful. Probably this is not what you want, and this is usually what people actually want. You should be using a dot to filter nested value. Okay. Now, this is for objects, right? So for objects, we can use that dot with my warning about if you try to use a nested object in your query. Now, what about arrays? I didn't say anything about arrays. So here too, MongoDB makes it convenient in the design. So what if now I have arrays in my data? So theories is an array of stuff, an array of strings. Then if in my query, I write theories special relativity, then of course it's going to return the documents for which theories is a string special relativity, but it's also going to return the documents where theories is an array of which one member is special relativity, right? So it's kind of flexible in that way. So it's also going to return the document that you see here, theory special relativity, because there is a match there. So you see that when you put a criterion with a key and a value, it's also flexible enough to handle array structures, right? I wanted to say something else here. Yes. Again, this is not SQL. It's not a high-level query language, and it might feel that some of the design decisions of the language are arbitrary or kind of you have to learn them by heart. Here are a few examples of things that you might think, okay, are arbitrary. For example, why 1 here? Why 0 here? That's how it was designed. You just need to learn it by heart. That 1 is for projecting and 0 for projecting away. Another thing that's arbitrary is the use of the $sign. Why the $sign was not something else, right? So this is part of the design, the fact that it's an array for handling the ORs. GTE to handle comparison. This is also some part of the design. Using null also for missing values is part of the design. The dot is part of the design. So there are a lot of things here, and also the fact that this also filters arrays. So it might seem scary at first that there are so many bells and whistles to the behavior of the language that look like that. That's because it's not so much a programming language as it is an API. This is more like a JavaScript API that allows you to execute queries on the documents. And in an API, you need to actually look at the documentation of the API in order to figure out how it works. And it's a lower level than a query language. So this is the reason why there are more things in here that seem arbitrary compared to, for example, SQL, right? But we are going to actually discover actual languages like SQL that do the same thing in 2 weeks, right? So we are going to, maybe even next week we'll start. So we will see actual query languages. But I still wanted to show you this first, because this is a technology that is widely used by everybody. And typically these queries, they are not actually going to be written by actual users, this find, blah, blah, blah. Typically, these queries are generated automatically by programs written in Java and Python that run against MongoDB, right? So this is not necessarily going to be actual people writing them. If you want actual people to write the queries, then you would prefer something on the level of SQL for most people, especially non-computer scientists usually appreciate having a high-level language. But I just wanted to tell you that so that you're not scared too much by the language. And I just want to give you the intuition that this is lower level than a language like SQL. Okay. I'm going to stop here. This we'll see next week the rest. But just what have we learned? We have a find function. The first parameter is a selection criterion. The second parameter is a projection criterion. And it will also work if your data is heterogeneous or nested, right? This is how you can use MongoDB. So next week, we'll look into a few more details of the language. We'll look into how it can accelerate looking up objects much faster than Spark. And then we'll finally look into the JSONic language and the RumbleDB engine. All right, it's exactly 10. So this is the time to stop here. So thank you very much for coming. I hope you enjoy the exercises that the TA team has prepared. Again, at the exam, if you want to focus on the programming part, you're going to have SQL as in PostgreSQL. You're going to have PySpark, right? RDD transformations with Python. You're going to have Spark SQL, right? And the fourth one is going to be JSONic, right? That we haven't seen yet. But just so you know, these are the 4 programming assignments that you'll have. With the TA team, we have prepared something. It's the first time that we do it in the big data lecture. Let's call it the big data magic box. It's basically a Docker Compose environment that contains all of the past examinations data sets, and that just works exactly in the conditions of the exam for writing PostgreSQL, PySpark, Spark SQL, and so on. So we'll put it very soon together with the old exams. And now you have you can enjoy not having to install anything as your predecessors had in the past years, and you'll just have these Docker Compose exam environments. All right, so thank you very much. And I'll see you again next week at 8 a.m. for the continuation. Thank you very much.